Good morning, afternoon, evening, whatever time it is for you watching this, and welcome to our notes on moisture and humidity. We are starting to really dive into meteorology, and we need to know about where hydrosphere meets the atmosphere, where the water on Earth starts to interact with the air around Earth. First, you're going to need to know about water vapor. Even though water vapor only makes up the 0 to 4% of the air at any given time, it is the most important gas for understanding weather and what's going on with weather. It's very important mostly because of how it absorbs heat. Besides being precipitation, water is very important as a heat absorbing gas. In order to change state, it has to absorb or release heat energy. Water is also kind of special because it can change from vapor to liquid to solid and back, all at temperatures and pressures that are found near Earth's surface. An important to unit, an important unit to know is going to be the calorie, which is actually a measure of heat or measure of energy. 1 calorie is the amount of heat needed to raise 1 gram of water by 1 degree Celsius. So when you look at the back of a bag of chips and it says there are 500 calories in a serving, maybe more like 160 calories in a serving for a bag of chips, that's a calorie with a capital C, which is actually a kilocalorie, but it's a unit of energy. When water changes state, you are adding or releasing heat, but there isn't actually any change in temperature. It takes quite a few calories to change ice to water and to change water to vapor, but that energy from those calories are then going to be released back into the air as the vapor condenses into water or water freezes into ice. So suppose I have a bowl of ice a bowl of ice water that is 0 degrees Celsius. The temperature of this bowl of ice water is not going to change until all of the ice has melted. All of the ice has to change state into liquid before the temperature of the liquid will start to rise. The heat that was absorbed went into breaking apart the molecular bonds of the solid ice. So even though I have my bowl of ice water sitting on the stove and there's heat being applied, that heat is going into breaking apart the solid, turning the solid into a liquid before the liquid can start to warm up. We call the heat that is involved in that temperature change latent heat. Latent means hidden. So this is the kind of hidden heat. It's not reflected in the temperature of the water. It's the heat that goes into breaking those bonds. So hopefully you're familiar. Solid water is ice, liquid water and gas, water vapor. Solid can melt to become liquid, which can evaporate to become gas, which can condense to become a liquid, and freeze to become a solid, which can sublimate to go directly to gas, and depose to go directly to solid. But this shows the latent heat that is being released. So when water comes and solidifies, it freezes and becomes ice, there is 80 calories of heat released. When water has to become water vapor, there's anywhere between 540 and 600 calories of heat absorbed, taken out of the environment, that will then be released when the water vapor condenses again. So there are a couple of different latent heats to be familiar with, and I'm sorry that my video is covering this. I can't make it any smaller. There is the latent heat of vaporization, same as down here. The latent heat of vaporization is the energy absorbed by liquid water in order to evaporate. So liquid heat of vaporization is that extra energy you need to break the water molecules apart to make them gas molecules. Then the latent heat of condensation, is going the other way, going from gas to liquid. That same energy that you absorbed during evaporation, you now release it back into the air when you condense. Latent heat of condensation is incredibly important for major violent weather. It has a huge role to play, and it transfers a lot of heat energy from the tropics, from the equator area, towards the poles. So the latent heat of condensation is an important one to be familiar with. There's also latent heat between solids and liquids. The latent heat of melting is the energy absorbed by solid ice, used to break the ice molecules into liquid molecules. And the latent heat of fusing releases that heat of melting to go back to a solid. Now we can get into humidity. Humidity is a kind of general term for how much water vapor is in the air. Air can't hold an unlimited amount of water vapor. Remember, air is the scientific term for the kind of specific mixture of gases that we have in the atmosphere, the 78% nitrogen, 21% nitrogen, 1% argon, and a little bit of other things. Humidity is how much water vapor can be held in the air. And depending on the temperature, that can be different. Saturation, you might have heard before in a couple of different locations or a couple of different contexts. When we're talking about humidity, saturation is the maximum amount of water vapor that can be held at a given temperature. So remember, temperature is also a measure of how much energy there is. So when the air is a warm temperature, there's a lot of energy. The air particles are flying around really fast, and there tends to be more space. So when it is hotter out, or when the air is a higher temperature, air can hold more water vapor. So air also is exerting a pressure. You don't really notice it because you've lived your whole lives feeling the pressure of this air. But when there is vapor in the air, that is contributing to the total amount of pressure you feel. So vapor pressure is the portion of the total atmospheric pressure that is due to water vapor. Humidity, there are two different main kinds that we'll talk about. There's specific humidity and there's relative humidity. Specific humidity is used less often. It is the exact weight of water vapor in an exact given mass of air. It is usually grams of vapor per kilograms of air. So this table on the side, it tells you the saturation mixing ratio at 0 degrees Celsius, 3.5 grams of vapor per kilogram of air is saturated. This is not the kind of humidity that you see on your phone when you look at the weather or that meteorologists are talking about on the news. This is not as dependent on the air temperature, and it is specifically in this cup full of air exactly how much water vapor is there. Relative humidity is what you are probably more familiar with. It is a percentage or a ratio of the air's actual water vapor content to the maximum that it can hold at a given temperature. A really helpful way to visualize humidity is to have a sponge handy. So this sponge represents all of the air in a given spot, and the pores within the sponge are the spaces that can be filled by water vapor. So if this sponge is curled up real tight, real close, I'm closing a lot of those pore spaces. There's not a lot of stuff to move around. This is colder air. If I were to dump some water or dip this sponge that's all curled up into water, it can't hold as much. When I let it out now, there's not nearly as much water in it. But if I take this sponge that's out loose, free, there's a lot more spaces in it. This is more like the air on a hot day. There's space to be filled by water. So I take this sponge and I can get it soaking wet. I can fill all of those spaces with water. So warmer air can hold more water vapor than colder air can. And if this warm air was cooled, I'm losing that water vapor. So all of that could be condensing and its precipitation. If the moisture levels stay constant, then the relative humidity will increase. So if the air is cooled, the moisture stays constant, relative humidity will increase. Imagine here, down here in the corner, I've got 10 degrees Celsius weather, 20 degrees Celsius weather, and 30 degrees Celsius weather. Warmer air can hold more water vapor. So here, this air, the yellow circle is showing the maximum amount of water vapor that it can hold. It's only holding 28% of what it can. So the relative humidity is 28%. If it were to get colder, but the moisture level didn't change, so now the cooler air can hold a little bit less water vapor, but the moisture level didn't change. There's still the same amount of moisture of water vapor in the air. That's now taking up a bigger chunk, so my relative humidity has gone up. If it were the other way, if the air was heated, there's now more space for water to take up, but the amount of water vapor hasn't changed, so I have a lower relative humidity. Relative humidity, is very dependent on temperature, and this is what meteorologists talk about. You can also see over here, this graph shows the amount of water in the air at 100% relative humidity. When it is entirely saturated, it is how much of the air is filled up with water vapor. There's another thing that can help figure out how muggy it's going to be outside on a given day, and that is the dew point. We know that when air is cooled, it can hold less vapor, but when air is cooled below its saturation point, then it's going to condense. So the dew point is the temperature to which air must be cooled in order to be saturated. So if it were 18 degrees Celsius outside, which I believe is around, I want to say 75 degrees Fahrenheit, with 70% humidity, that means down at around 14 degrees Celsius, we've got our dew point. And anything less than that, that is where, if the moisture levels stayed exactly the same, we just dropped it down to 14 degrees Celsius, there would be 100% relative humidity. If I tried to go any colder, then the air can't hold that much moisture anymore and it condenses. So if air is cooled below the dew point, condensation occurs, you get clouds, fog, precipitation. But frequently, people use dew point to kind of give you an idea of what the weather outside is like. Say it is an 80-degree day. Then if the dew point is 50, that means you're a long way from the air being saturated with water vapor. So it's not going to have a high relative humidity. It's going to be fairly pleasant out. If you get into 70s or 75 or even getting much closer to 80, then the air is almost saturated. The amount of difference between how much water vapor can be held at 80 degrees and at 75 isn't very different. So if you've got 90% humidity down 5 degrees, it might become 96% humidity. So having a high dew point means it's going to feel a lot muggier, sticky, oppressive humidity. So dew point is often used as another way to explain how humid it is outside. Lastly, you need to be familiar with how do we get exciting weather phenomenon? You need the air to be lifted in some way. There are a couple of different ways that stable air can be forced upward to make exciting clouds and precipitation. We are going to talk about 3 different types: orographic lifting, frontal wedging, and convergence. We're going to talk next week more about clouds, precipitation, warm and cold fronts, and then we're going to start to get more into what's going on exactly with this exciting severe weather. So orographic lifting is moving up and over land. Typically, you have moist, warm ocean air being lifted over a mountain dry air is descending. But orographic lifting is when air is being forced up and over elevated terrains. Remember when we talked about mountain building? Oro means mountain. Orogenesis was the birth of a mountain. So orographic lifting, the air is being lifted upwards by mountains or elevated terrains. If that warm air contains moisture, clouds or possibly precipitation could form, because as the warm air rises, it cools and condenses and it can rain. And then you get more dry air descending on the other side. Frontal wedging is when you have a cool air mass acting like a barrier and a warm, less dense air mass rises in front of it. Like I said, next week we're going to talk more about different air masses and how they act. Again, if the warm air contains moisture, as it rises, it will cool and possibly condense to form clouds and precipitation. Lastly, there's the convergence uplifting. This is where you have two air masses colliding and it creates an upward flow. It's two things running into each other and getting pushed up. Again, kind of like mountains forming. So again, if the warm air rises and contains moisture, it can condense and form clouds and possibly precipitation. So next week, we're going to talk more about different kinds of clouds and precipitation, and then we will be getting more into tracking weather and severe weather. Enjoy your evening. Bye.